Good afternoon, everyone. Geographic information systems and machine learning can improve our understanding of medfly spatial distribution in complex agricultural systems, enhancing and refining our management of this economically important pest. Adult medflies are mainly the target in management programs, and area-wide programs for this pest has shown promising results. Normally, area-wide management programs for medfly cover large areas, trying to target all individuals, but this poses financial challenges, especially in the South African context. However, there's been a shift towards a new paradigm of area-wide IPM, where pest management or pest populations are managed more precisely by following their spatial and temporal distribution patterns. With this in mind, the when, where, and why questions regarding the spatial distribution of medflies becomes important, and therefore the aim of this study was to investigate the spatial distribution of these flies, to find out where they are, when and where they are spatially, and why. So to do this, I used long-term area-wide medfly trapping data from 399 traps indicated on this map, which was monitored on a weekly basis for 30 weeks for 4 consecutive seasons in the EGVV region. I used GIS and spatial analysis to quantify the spatial distribution of medflies, and machine learning to explain the spatial distribution. Hotspot analysis, which is a type of spatial analysis method, were used to quantify the spatial distribution of the medfly trap catches. So trap catch were aggregated into 1 square kilometer blocks indicated on the map on the left. Yeah, there you go. And the blocks were used to express the hot and cold spots. Looking at the map on the right, hot spots are areas where blocks with high trap catches clustered together, and cold spots are blocks with low trap catches clustered together in space. And just so these hot and cold spots are determined by statistically by a statistic called Getters or GIS star statistic. So monthly and seasonal hotspot and cold spots were calculated. However, I would just want to draw your attention to the March and seasonal results. In both the March and the seasonal map, there is a clear split in the spatial distribution of hotspots in the southeast and cold spots in the northwest, indicating that underlying spatial processes are at work. Exploring this result, we found that the same split occurred in the spatial distribution of long-term temperature on the left and long-term annual rainfall on the right. This suggests that cold spots occur in areas with mild temperatures and high rainfall, in this case the northwest of the line, while hot spots occur in hotter, dry areas, in this case in the southwest of these lines. And this is also supported by other research. However, to further support this result, we studied the relationship between hot and cold spots and or the spatial distribution of hot and cold spots and a set of geographic variables. And machine learning proved to be valuable in modeling the relationship between the hot and cold spots and a set of geographic variables. So if we focus our attention on the March model, it showed that the spatial distribution of long-term rainfall in the EGV area explained 80% of the spatial distribution of hot and cold spots. Now what this means is that we found that there are a spatial relationship between medfly trap catch and the geographic characteristics of an area, and this information can be valuable for area-wide program managers to conduct more precise spatial planning, which could lead to better program performance and reduced costs. And finally, using geographic characteristics of an area rather than focusing on highly variable seasonal factors presents a proactive approach in assessing medfly risk. Thank you.